Welcome to the channel Professor Da Vinci. Hello everyone, I am the professor. Subscribe and hit the notification bell to stay updated. Today the video topic is derivatives, the mathematical background of machine learning for optimizing your models. So this video discusses the importance of derivatives in machine learning models. Importance of derivatives. In the realm of mathematics, there exists a branch that reveals the hidden dynamics of change, a field that offers a profound understanding of a rate of change, and that is derivatives. Derivatives are cornerstone of a calculus, are not just abstract symbol or a mathematical tool. They are the language in which we describe the natural words, ceaseless transformations. For simple act of calculating the speed of a moving car to intricacies of modeling complex systems in physics, economics, and engineering. Derivatives are omnipresent, empowering us to interpret the ever-shifting landscape of our lives. Derivatives provides a means to explore how function evolves as its input value changes. At their core, they answer questions like how fast is an object moving at a moving point of time, how fast the object is moving at a given point of time, and what is the instantaneous rate of change of a quantity. A deeper understanding of derivatives offers a lens through which we can view the world with unparalleled clarity, enabling us to quantify, predict, and control the dynamic changes that defines our existence. Now let us discuss how these derivatives help in machine learning. Derivatives play a crucial role in machine learning in several ways, particularly in the context of optimizing and training machine learning models. Here are some key ways in which the derivatives helps in machine learning. The first one is the gradient descent optimization. The first one is gradient descent optimization. It's used in machine learning to minimize the cost function by adjusting model parameters with derivatives. The next is backpropagation in a neural network, a technique in deep learning that calculates the gradient for a neural network layer, enabling error-based learning and parameter adjustments. Next, feature engineering. Derivatives can create a new features from data, revealing the pattern and the trends useful for tasks like anomaly detection and forecasting. Next, regularization. Techniques like L1 and N2 regularization use derivatives to add penalty terms, promoting simpler and more stable model parameters to prevent overfitting. Next is sensitivity analysis. Derivatives help understand how small change in an input or parameter impact model predictions, enhancing interpretability and reliability. Hyperparameter tuning. Derivatives guide the search for optimal hyperparameter in machine learning models, improving model performance. Dimensionality reduction. Derivatives are used in a technique like a PCA to reduce the data dimensionality while preserving the essential information. Natural language processing. Derivatives play a role in training language model, optimizing natural language processing NLP model like BERT. Reinforcement learning. Derivatives assist in determining optimal policies and value functions, helping agents make decisions in a complex environment. Let's see some example of derivatives. Let us take the function f of x equal to 3x square minus 2x equal to 5. To find the derivative of the function f of x with respect to x, we have to use the power rule for differentiation. So what is the power rule? Power rule states that if the term is in the form of x power n, then the derivative of x power n with respect to x is this is the power, and this is the base, this is the base, and this is the n is the power. So if your term is in the terms of x power n, then the derivative of x power n with respect to x become, first we need to have the power base power minus 1 and the derivative of base. What is the base here? X. Derivative of x is 1. So we yield derivative of x power n with respect to x equals n x power n minus 1. So here come to the function. So we have the function f of x equals 3x square. So if we want to derive this 3x square, so how it becomes? So first we need to have the power, and we have the base of 3 and the x, then power minus 1, and then minus. So for this term, what is the power? Power is the x power 1. So we get 1 product of 2, 1 times of 2, x power minus 1. So which equals 2 times of 3 is 2 times of 3 is 6, x power 1, that is 6x minus 2 times of x power 0 is 1. So the derivative of f of x with respect to x, so the derivative we can say is f dash equals d of 6x minus 2. So we can also say that derivative of d by dx of f of x equals 6x minus 2. So this can be referred like this: f dash of x equals 6x minus 2. So this is f dash of x is called first derivative. Let's explore the maximizing the profit in manufacturing. Suppose you manage a manufacturing company that produces a certain type of a widget. Your profit function is given by profit function. So I can take this. A profit function is a p of x equals minus 2x square plus 100x minus 2000, where x is the number of widget and the p of x is the profit function. To find the maximum profit, these steps have to be followed. First step is to find the derivative of the profit function p of x, which is denoted as a p dash of x. The second, need to find the critical points of the profit function, where we need to assume that derivative of p of x with respect to x equal to 0. And then the third step is to find the second derivative, and finally interpret the result based on the step 3. So how these derivatives help in their real life? Let us take the maximizing their profit in manufacturing, as said earlier. So we have here the profit function of a p of x. P of x is equal to minus 2x square plus 100x minus 2000. So we need to find the derivative. So that is p of x. We need to find the derivative. That is p of x equals derivative. First derivative is say with respect to d by dx of p of x. So which comes here. So we yield this power base into power minus 1, base power minus 1, like that. So minus 2 times of 2 times of power base power minus 1 plus here 100 derivative of x is 1. So we yield the first derivative of a product function p of x equals minus 4x plus 100. This is the first derivative. Second step, we need to assume that is the first derivative p dash of x. So this is a p dash of x. P dash of x equal to 0, meaning we need to equal 4x plus 100 equals 0, which implies that x equals 25. So how x equal to 25 minus 4x equals bringing 100 to other side, and x equals minus 100 divided by 4. So we yield x equals 25. So second step, assuming that p dash of x equals 0, and we found the critical point x equal to 25. After that, find the second derivatives, that is p double dash of x. So we need to find the derivative of this one, second derivative. So minus 4x plus 100, which yields this second derivative is minus 4. So since p second derivative, 2 times double derivatives of a p of x equal to minus 4 is a constant value, that is negative 4, which implies that the critical point at x equal to 25 corresponds to maximum profit. So that means whenever the x equal to minus 4, we yield the maximum profit on the curve. So putting the value here, putting this x value to the product function. So p of 25 equals minus 2 times of 25 square plus 100 times of 25 minus 2000, which yields the 1250. The ideal level of the maximum profit is 25 widgets. So if we produce 25 widgets, we will get the maximum profit. So the maximum profit is 1250. Maybe it may be the euro or whatever the currency, and it is achieved by producing 25 widgets. So this is how the derivatives helps in our real world, real time. Let us discuss how the derivatives helps in the machine learning. So let us take a small example, derivatives in a linear regression model. So derivatives are commonly used in machine learning for tasks like optimizing model parameters and calculating gradients. Here's a sample exercise involves derivatives in the context of machine learning. In linear regression, you have a data set with the input feature x and the target value y, and you want to find the best fitting line that minimizes the maximum mean square error. The linear regression model can be presented as y equals beta naught plus beta 1 of x times x, where y is the target variable, beta naught is the intercept, and beta 1 is the slope. So the mean square error MSE is defined as mean square error equal to 1 by n summation 1 to n yi minus beta naught plus beta 1 xi power 2. The task is to find the gradient of the mean square error with respect to the model parameters beta naught and beta 1, so that we need to minimize the mean square error. So let us see how this derivatives helps in minimizing the mean square error in the next step. Let us take the x is the, let us take my pen. Okay, right. So here derivatives in a linear regression model. So first, derive the MSE with respect to beta naught. So already we know that MSE it means square error equals to 1 times of 1 divided by n, summation of I equal to 1 to n yi minus beta naught plus beta 1 xi the whole square. So first we need to find the derivative of MSc with respect to beta naught. So this is actually here we have two things, beta naught and beta 1. So we need to here do the partial differentiation. So partial differentiation is this one. This is a partial differentiation with respect to beta naught. So beta naught of MSc equals, so we can say that, so we need to find the beta naught, partial differentiation of beta naught, the powers here, so 2. So we get power and the base, so 2 by n, summation of I equal to 1 to n. We have yi minus beta naught plus beta 1 xi power minus 1, that is power 1, and the derivative of a base is here, the base, this minus derivative of a beta I, so this is the minus 1, and which is equal to minus 2 by n, summation of I equal to 1 to n yi minus beta naught plus beta 1 xi. And after finding the partial differentiation of beta naught, now find the partial differentiation with respect to beta 1. Same partial differentiation with respect to beta 1 for the MSc. So we get 2 by n, so here it is a positive sign, so it is a 2 by n is the summation of I equals 1 to n yi minus beta naught plus beta 1 xi to the power 1, so minus xi. So here we are going to with respect to beta 1, so beta 1 is the derivative of the base, so beta 1 becomes 1, and this xi is a minus symbol xi. So this is the partial differentiation of MSc with respect to beta 1, and finally we get this multiplication of a minus symbol comes here, minus 2 by n, summation of I equal to 1 to n yi minus beta naught plus beta 1 xi times of xi. So this is a partial differential. So these gradients can be used in a gradient descent algorithm to iteratively update the model parameters beta naught, beta 1 in order to minimize the MSc and finding the best fitting line for the linear regression model. So this is how the derivatives helps in the machine learning. So forthcoming video we will explain the more in detail of derivatives, gradient descent algorithm. See you, bye bye, have a nice day.